Good afternoon. Many thanks for the introduction and for the invitation to this exciting workshop. After the mind-blowing perspectives of ever complex integrated circuits, in this talk I will take actually a step back and look a little bit more at the physics of the basically spontaneous emission, which can be used to generate single photons. Is this working, by the way? No. So this is work which has been done mainly in my group at the Eindhoven University of Technology in the Netherlands, and we also have a collaboration with a group of Verhagen in Movable, also in the Netherlands. Okay, so what is this about? Well, it's about single excitons in semiconductor nanostructures, which are able to generate single photons, and they can do this in principle very efficiently. This has been demonstrated experimentally, efficiency exceeding 90%, and those photons can also be very indistinguishable. So in principle, they are a very important source for quantum photonic applications. Now, of course, they are have been used for fundamental studies of quantum optics, and of course, for quantum information processing as a whole. Now, most of the time, a quantum dot is not enough because quantum dots are radiating in all possible directions, and you want to collect all those photons. So typically, what we do is put them integrate them inside cavities. For example, this photonic crystal cavity, where we define a mode, and then interaction of the quantum dot with that mode is more efficient, faster than interaction with any other mode. So that basically we can funnel all these photons into the cavity mode, and they're into a waveguide and so on. So we get increased efficiency, and on top of that, because we increase the spontaneous emission rate, therefore we reduce the spontaneous emission time, and therefore we increase the coherence. Now, of course, the coupling of this emitter with the cavity mode determines how good the source is. And this coupling has two parts: a spectral part, so energy matching, and a spatial part. Of course, I need the quantum dot to be in exact right position in order to do this. Now, on one hand, this is a challenge to make reproducible single photon sources, a challenge we have been fighting with for the entire community for a long time. This challenge is actually pretty much solved. But I'm not going to talk about this today. I'm going to talk about the opportunity that this matching, particularly the spatial matching, brings in order to actually control that process of spontaneous emission, and thereby actually do more than just generating single photons. And here I want to talk specifically about the possibility of dynamically controlling the spontaneous emission process. Actually, nearly everything that has been done so far in the system, so the solid state cavity QED system, has been static. So there is a structure, it's maybe tuned in some clever way, and then I shine a pump laser on top of it and get photons out. So I have no control over the interaction process. Now this brings a number of problems. The first is that we actually cannot control the photons which are emitted, particularly in time. So for example, out of such a system, when it's a weak coupling regime, essentially you get this kind of photon waveform out, so a fast rise and a slow decay. Well, you can change the rate of that decay, but you cannot change the shape in general. Now, for example, this is a problem whenever you want to incouple that photon into another system. So we heard earlier today about how important it is to actually, at least in the photonic applications, to actually have a communication and that direct coupling between two quantum processors, something like this. So this is impossible if or exceedingly difficult if the temporal waveform is asymmetric. Also, if I want to use the interaction of light and matter in a linear way, then I'm going to operate in this strong coupling regime where basically exciton photons exchange energy. And then the problem is, yeah, it can be very nice, it has been demonstrated, but at this time we have no way to actually control that process. So for example, we cannot control Rabi oscillation, and for example, stop the interaction at the time where we create an entangled state. This is, of course, what has been done in atomic cavity QED, but not yet in a solid state. Okay, so if we can achieve dynamic control, we could actually solve most of these problems. This is just an example, a couple of examples. Now, what can we do to control this interaction? Well, one thing was about the spectral matching. So, of course, we have an emitter, let's say at this wavelength or energy and the cavity mode, and well, they will only interact if they are at the same frequency. Now, there are a number of ways you can control the frequency. In quantum dots, we can apply electric fields that will result in a star tuning of the energy levels. You can also control the frequency of the cavity, for example, shining a laser on top of it, that changes the index and changes the frequency. So a number of years ago, we worked on controlling that tuning dynamically, so fast. So the idea is, again, you have a quantum dot and a cavity. In this case, we were trying to tune the quantum dot's energy, and we in and out of the cavity. And that will initiate or stop the emission process. So to do this, we developed a technique of photonic crystal cavity diodes, which can operate at high frequencies. This is challenging, of course, because of a photonic crystal platform. And we managed to demonstrate that you can alter the emission process in such a way that you go, for example, from a simple exponential waveform that you will get in a normal system. Well, if after pumping, at some time delay, you change the tuning between the quantum dot and the cavity, you have to do it with more than 1 gigahertz bandwidth, then you can actually increase, for example, the emission rate. And now in this system, optimizing things a little bit, you could actually generate even asymmetric waveform. So this is feasible. However, there is an interesting problem. You can control intensity profile, but because you are operating with frequency tuning, you will produce a phase jerk. And now this phase jerk will be asymmetric in time and will give you essentially the same kind of limitation that you have to asymmetric intensity. So we need to look into different directions. And well, the question is, can we control this interaction without playing with frequency? Now, if you think about it, it actually should be possible. The interaction of an emitter with a cavity is set by Rabi rate, what we normally call G, and that is essentially proportional to some property of the emitter, dipole moment, and to the vacuum field or the mode field at the position of the emitter. So if you have a situation purely hypothetical, you have a given cavity, you have an emitter inside, and then there is no field at the emitter position, there will be no emission. If you now perturb the cavity in some way, you actually create some field at the emitter position that will actually turn on this process. Now, if you can do this fast enough, you are in a good situation. Now, the problem is, how do we control the field? And again, we want to control the field without changing the frequency. Otherwise, we get back into a frequency churn problem. Now, this is actually a very simple electromagnetic problem. This is essentially the equivalent of the Schrödinger equation for electromagnetism. It's the wave equation written as an eigenvalue problem. Be careful, this is not the Hamiltonian, but the magnetic field. And well, we know that whatever we do will be a perturbation of the electric constant. So actually, we're dealing with a perturbation problem. And we know from quantum mechanics that it's very easy to calculate the result of perturbation. There is normally a perturbation frequency, which here will end up here. And that perturbation frequency is related to the diagonal matrix element of the perturbation. And this is 99% of what we do, actually, in photonics. But we can also, a perturbation can also perturb the field, the eigenfunction, in our case, the field. And what is interesting is that this textbook expression of the perturbation has different matrix elements, the non-diagonal matrix. So that means that it's in principle possible to control the effect of a perturbation on the frequency or on the field separately. Particularly what you want to do is, assuming you want zero frequency shift, you want to make this zero and the non-diagonal matrix element non-zero. And also you want to you have to look at the unperturbed eigenstates and make the frequency difference as small as possible, because this will maximize the effect of the perturbation on the field. So this means we need a photonic structure where we can apply perturbation with the right symmetry, and we want to use structures where there are number of modes close in frequency. Now this brings to the situation of using coupled cavities. And actually this is a 3-cavity system. It's the best one we found, and Mark already showed it for a completely different application. I'm not sure you can see the color very well. These are 3 photonic crystal cavities. So you see the holes here, and there's one here, and one there. And now we start from a situation where the photonic crystal cavities are resonant, so they have exactly the same frequency. In this case, of course, there are 3 eigenmodes, as Mark mentioned, and one of the eigenmodes has an interesting property that it has 0 field in the center. It's just due to symmetry. If I now perturb the index in the 2 lateral cavities in an antisymmetric way, I'm applying an anti-symmetric perturbation, and the result of that will be that the field I will get, for the same mode, I will get field in the central cavity, but the frequency will not change at all. And the reason is that the diagonal matrix element of that perturbation is 0. Okay, by the way, this is, of course, is actually well known. The properties of these ways are well known. Now, what it means in a more general way, you have these 3 cavities, and you look at the 3 eigenmodes as a function of the tuning between these 2 lateral cavities. And now our mode of interest is this one. As you see, is completely dispersionless. But if we look at how much field this mode has in the what we call the target cavity, well, this field goes to 0 at 0 detuning. Now, because the G is proportional to the field, at the emitter position, if we have our emitter there, at 0 detuning, you will see no field, and therefore it will not emit. It will not interact with the mode. And that is a pure field modulation with no churn. Now, this is something that we call mode field modulation. And I want to show you a couple of examples of how this can be done. One is experimental, one is an experimental demonstration, theoretical experimental demonstration. So it's theoretical, but I will start with the theoretical one. Sorry, with the experimental one. So we made these 3 cavities, 3 photonic crystal cavities, and we don't use 3 identical cavities because we want to tune the 2 lateral cavities without perturbing the central cavity. So we use very long lateral cavities, and then in the center here, actually vertically coupled, you have our target cavity, and this is where we pump the emitters. So in our experimental setup, we pump the 2 lateral cavities thermally for the moment. So we just heat them. By this heating, we produce a refractive index change, and of course we can bias, so we can put some static value, and then we can increase and decrease. So we can create an antisymmetric perturbation throughout. And then we pump the central cavity, and we collect light from the central cavity. Now, when we do this, we plot the photoluminescence spectra that we measure as a function of the power on the left, and then, well, the one on the right is equal, but opposite. So you can see this as a function of detuning. And we see 3 modes, and this is what we're supposed to see because there are 3 modes. But the interesting thing, if you look at this mode, so first of all, it does not tune almost at all throughout the entire range. But the most interesting thing is that if you look at 0 detuning, there's no emission. So the intensity of the photoluminescence goes to essentially 0, and this is because that mode has no field. Now, to show this in more detail, basically we plotted the intensity of this peak as a function of detuning, and we also measure the decay rate, the spontaneous emission decay rate at different tunings. And this is what you get. So again, the PL intensity of that mode goes to 0, and the spontaneous emission rate decreases. Of course, we cannot measure it here because there is no light, there is nothing to measure, but this fits very, very well with our model. So we are confident that essentially we are modulating the G value, so in the interaction between an emitter and a cavity from the max value. So basically out of resonance, we have essentially the modes very confined in that cavity to 0. And this is, of course, also corresponding to the simulations of that particular system. Now I want to stress here, modulation is slow because it's thermal. But in previous work, we have shown, as other groups also have seen, that we can, with shining laser pulses on the system, we can inject free carriers. Now we have the modulation essentially instantaneous, and then leave stir for a few hundred picoseconds. And that is what we are doing now to repeat the same experiment, but now modulating two cavities by inductive frequency. Okay, now what can you do with this? And I'll switch to some theory. Essentially, you can do whatever you want, because now you have the control of G as a function of time. So it's like people working on atomic cavity, they're throwing atoms at different speeds. And what we will do there, instead of controlling interaction time, we will control G as a function of time. So for example, this is a simulation of what you can get out of your single photon emitter in the case where there is no control, so I get fast rise and a slow decay. If you can control the G as a function of time, then you can actually make this map basically a nice symmetric waveform. And all this with no chirp. So basically that would lead into generating single photons which are temporally symmetrical. Okay, now I switch gear a bit, I go into some theory, and I want to show you what we can do with this mode field tuning or modulation when we use a mechanical degree of freedom to actually make the tuning. So imagine the system, again, 3 coupled cavities coupled by semi-transparent mirrors. And then we look at this mode, again, this anti-symmetric mode, which has no field here. And now we assume that these mirrors can move. But we will look at a specific kind of motion where essentially we make the 2 mirrors rigid so that they have to move together. Okay? Now imagine the system now, if these are moving on this side, essentially it will produce, on that side it will produce a negative frequency change here, a positive frequency change here. Thereby, I actually have an anti-symmetric frequency shift in the 2 lateral cavities and no shift here, which is exactly what I need. So that will create a field in the central cavity without detuning my system. Now you can say, okay, how can you do that? So in a microscopic system, of course, but maybe I want to do it on a nanomechanics platform. Well, this is actually perfectly feasible. If you look at one standard optomechanical system, which is photonic crystal cavities in a nanobeam, and you define the photonic crystal cavity by slightly changing the characteristic of the holes around the regions where you want them, and you don't see the field, but the same modulation is made here, here, and there. So there are 3 cavities, but again, this is the modes, anti-symmetric modes, so that it does not feel that. And now, if you look at these cavities, the nice thing is that there are also cavities for the phonons. So there are localized mechanical modes, and these breathing modes, they actually hybridize as well as the same way that the optical modes do, and therefore you get one of these coupled eigen modes of the mechanical system, which is breathing here and there oppositely. And therefore this gives us exactly a tuning, a negative tuning here, a positive tuning there. So we get this essentially for free. Now in this system, again, the same story. The modes, one mode will be perfectly dispersionless. So in terms of optomechanical dispersive coupling, that is 0. But the field is varying actually linearly with the position, with the tuning, therefore with the position in this region for that mode. Okay, so nice. What can we do with that? And well, I will show a couple of Hamiltonians. So again, this is standard Jenkins Hamiltonian. But now the thing is, G is a function of the field, and the field is a function of position. So essentially, when we have a mechanical displacement, we vary the field, and therefore we vary G. And this variation, well, in general, I will linearize it. So I will look at the linear term here. And thereby my Hamiltonian splits in 2 parts. One is, well, is related to the steady state value of the G. And the other one has the position operator inside. So I have the operators on my emitter, on my cavity mode, but also the position operators. Now this is what we call mode field coupling. So it's a kind of new way of the mechanical coupling. It's not dispersive, it's related to the variation of the field. The rate of this coupling is simply related to how G varies with position. Now the nice thing is that if we adopt this particular mode, this part is 0. because there is no field. If we operate around resonance, there is no field. Okay? So the only interaction with the emitter, between the emitter and the photon, will be mediated by this term. Okay, so let's have a look. Essentially, if you look at this Hamiltonian, you see that it can only produce transitions between states which do not concern the phonon number. So you need to change phonon to make a transition. So it means that if you look at the combined eigenstates of the emitter and the phonons, we can produce states from the ground to the excited state by increasing one photon number or by decreasing one photon. So essentially what these are just, the physics is very similar to phonon sidebands in semiconductors, in systems like nitrogen vacancy sensors. But here it's related to a macroscopic and thereby engineerable mechanical vibration. Okay, so it's a tripartite interaction, and in principle, what you would like to see is that we have a tripartite vacuum radio oscillation where we start with the emitter being in excited state, and then it decays by emitting, for example, one photon and one photon, and then etc., etc. Now, is this feasible? It's difficult because we can show that that rate, well, we can give a simple expression for that, which depends on the G, so on the radio rate, and on the optomechanical coupling rate of each cavity. And essentially, the numbers there are such that the period this vacuum radio oscillation will be in the microsecond range. And that is pretty difficult to observe because, of course, the coherence will occur much more quickly. So there is another route we can take. We say, well, we pump the optical mode, so put a large classical drive, and at that point we are left with an interaction Hamiltonian between the emitter and the photons. And guess what? This Hamiltonian is identical to the James Cummings Hamiltonian. So that means that we can take all nice things we know about basically standard quantum optics, having BQIT, and then apply them to the atom-phonon interaction, which is mediated by the field. And now, the very interesting thing is that this is controlled by the number of photons. So you have a knob to actually control that interaction. An example of what you can do with this is you start with an excited atom. Initially, nothing happens. If you bring in a field, you switch on the interaction with the photons, and you can actually produce essentially a single photon and just one photon, so exactly a single photon state with that system. So it acts as a single photon source. Okay, so lots of things you can do in principle, of course, entangle cavity and atom and mechanics and so on. And to cut long story short, essentially we have the optical cavity, the photons as information carriers, the quantum emitters for non-linearities. The mechanics is often seen as a possibility for a memory, and this mode field coupling actually allows you to couple the quantum emitter and the mechanics directly. In conclusion, mode field modulation is a new tool that we have to play around with solid state cavity QED, and there are also managerization possible. Of course, circuit cavity QED, you can do exactly the same thing, maybe much easier even. And you can think of using this kind of approaches more generally in quantum systems. Thanks for your attention.
Any questions? So your mirrors need to be in the ground state, right, for this to work.
Yeah.
What is the prospect of that happening?
Yeah, this is, we know that there are optomechanical systems of this type have been put very close to the ground state, and there is a lot of work ongoing in that direction. These are gigahertz frequency mechanical oscillations, so it's actually not that dramatically difficult. Of course, it's not 4K, it's lower. And of course, and by the way, you can also use this process to actually cool down the mechanics. So instead of the standard optomechanical dispersive cooling, you can use that as well.
Any other questions? So in the other demonstration before, you were tuning the two side cavities. You mentioned about injecting carriers. Can you also optically tune these cavities, and this could be very fast.
Yeah, absolutely. This is what, so we are doing this optically, so we would inject the frequency optically.
Okay.
We did it. I can show you in a 2-cavity system. We did it a few years ago, and this is what we got in terms of spontaneous emission. So we had a situation where 2 cavities were on resonance. We were bringing that off resonance, and then we get a peak in spontaneous emission. You see this 200 picosecond, which is limited by the time that the cars remain there, and then effectively you could bring this down by a factor of 10 just applying electric field to sweep out the cars, as is done in silicon modulators. And eventually you could use a K3, and that would become, of course, the instant tanks. But of course, there the amount of tuning you can make is quite smaller, so that's a challenge.
Thank you.
Any other questions? No? Oh, yes?
So there's some other optomechanical systems recently have been using some more like 2D materials. Can you think of it's easier to put these into the ground state. Can you think of a coupling between these and the quantum dots that you might be able to use for this kind of scheme?
This kind of scheme, I'm not sure. Maybe we should discuss.
Okay.
All right, if there are no further questions, we'll thank Andrea again. And just to let you know, we're going to reconvene after the break. And